I don't know.
Okay.
I just arrived.
I would say just few.
Oh, that's great. Thanks.
Okay, so you met Matthias Wachter.
Yeah, it's.
And you are the head of the group about stochastics.
Yes, that's true.
Inside of TWIST.
Yes.
And TWIST means turbulence, wind energy, and stochastics. Okay. And this TWIST is headed by Joachim Pinker, as you know it. Inside of a consortium called 4Wind. 4Wind is a consortium. Yes, there it is. So, okay. You guess what I would say. And of course, they are based at University of Oldenburg. Okay. So
Thank you, Daniel.
the floor is for you.
Thank you very much. I'm happy to be here, and I'm happy to give a seminar. And this is a little bit about everything under the roof of wind energy and turbulence, and why we need to understand turbulence to go forward to proceed actually in wind energy. So yeah, everything here was explained already, so we can do a small step forward to 4Wind. 4Wind is actually a cooperation between 3 universities in northern Germany, which is Oldenburg, Bremen, and here is Hanover. But 4Wind as a university cooperation now has joined into the very great name of Research Alliance on wind energy. It's, as you see, it's black, red, and yellow, so it's a national alliance together with DLR, the German Aerospace Center, and Fraunhofer IWIS, which is, Fraunhofer is, as far as I know, the greatest institution for applied science in Germany, so it's not a university, it's applied science. And yeah, there are of course several institutes in this collaboration. I don't need to name them all. So we tried to form larger clusters of institutes in order to be honest, in order to have a stronger position in getting funding, and to be not so honest, in order to have the best results possible. But I'm today going to talk about more or less 3 topics. By the way, this is a rather long talk, about 1 hour as far as I remember. So if you have the time, I can show everything, and if you prefer to, I don't know, have lunch or whatever, we could try to shorten this a little bit because it might be like
if you can do it in 45-50 minutes in order to have questions after that.
Yeah, let's see.
Yeah.
Okay. So it has 3 main topics, a little bit of basic features of turbulence, and a little bit about wind turbines, how do they work, and a little bit about their operating conditions, which again points back to turbulence because they operate in atmospheric turbulence. Let's go ahead. Well, that is the operating condition, so we connect turbulence and turbulence. Going ahead to the Navier-Stokes equations, which is the well-known set of equations governing turbulence as a problem of classical physics. The equations are well known, and it is also well known that it is still not clear whether smooth, physically reasonable solutions exist for this set of equations, which is a fascinating problem in physics. Most of the remaining problems in physics are rather into quantum physics and other advanced topics. This is classical physics. There is no H bar in any of the equations, and still it is not solved. In an analytical way, I have to say. one important aspect of these unknown solutions is derivation of velocity components with respect to space as well as time, but it's to some degree interchangeable. So derivatives, of course, are somehow the limit of differences divided by the separation if we try to make the separation as small as possible. So the smooth transition of this slope-like quantity in the case when r approaches 0, that is actually one aspect of the challenging physics of turbulence. We call it the velocity increment, that is the velocity difference over a fixed separation in space or time. And with this we can write u r over r and take the limit. And this is one of the aspects we like to understand. The nice thing is that this aspect is more or less accessible through measurements, through experiments. So there exist nice devices to measure velocities in turbulence experiments, and we can directly investigate this quantity. So we have some experimental access to this aspect of our problem here. What am I going to say? Okay, yeah, known results so far. Block my space. We go back to Kolmogorov in say beginning and in the middle of the last century, and also on this side to Richardson. The picture of Richardson's cascade was that in turbulence we have large structures like eddies, or they might be more complex, but not necessarily be a circular eddy, but some flow structure which tends to break up into smaller flow structures and even smaller, and this takes on until we reach on a spatial scale the dissipation range, where the structures become so small that they are dissipated into heat. This is understood as, or I'd rather say this is considered as a turbulent cascade, where we transport the kinetic energy from large scales to smaller scales, from the integral scale to dissipation scale, and we observe some change in the shape of the increment PDF. This is actually the PDF of the UR, that is the velocity differences over a scalar. So we see that on the large scale, which is here the integral scale, we have an almost Gaussian shape. Please note that this is a logarithmic scale. In the logarithmic scale, a Gaussian is a parabola, because we have exponential of minus x squared or something. And to the smaller scales, close to Taylor and the dissipation scale, we have a non-Gaussian, rather heavy-tailed PDF. That means extreme velocity differences extreme changes become more and more probable compared to a Gaussian distribution. So this is a thing we in Oldenburg like to call intermittency, the deviation from the Gaussian PDF. It is clear that it is not, there is not a unified definition of intermittency, and from the theory of Kolmogorov, we would rather say intermittency is a degree of multifractality of scaling exponents, nonlinear behavior of scaling exponents. Both effects are tightly connected, but if I say intermittency, I would directly speak of the heavy-tailed PDFs, just to keep things simple. Okay, let's move on. Now we come to atmospheric well, at least for this example, this is an example of an atmospheric PDF of velocity increments, where we clearly see this intermittent shape, and compare it to a Gaussian. In atmospheric turbulence, we have typically very strong deviation from the Gaussian distribution. There are several reasons for that, but here if we go to beyond 5 sigma, we see we have many orders of magnitude actually of the difference. So we see that especially in the atmosphere we have non-Gaussian statistics for small scales, but in the atmosphere we have them for all scales. We call this intermittency. I think that's all on that slide, yes. So how to attack this behavior of the velocity increment? Velocity increments are typically two-point quantity. That means we measure the difference between 2 points. We have the UR, the velocity difference here. Of course, we have in this Leonardo da Vinci sketch, we have already visible that it's a whole lot of complexity, and with only 2 points we will not catch it. So there is something missing, and in the general case we would need an arbitrary number of points and somehow characterize the joint PDF, the joint probability distribution of all our arbitrary number of points, and we can clearly transform the velocity, the joint velocity distribution of all these points into a joint velocity distribution of increments, that means of differences. If we have all the differences and a single absolute velocity, we would have the same information as in all the velocities. I think that's more or less trivial. This would be fairly complete information, but to be honest, it is rather impractical to measure an arbitrary number of points and to make an arbitrary order statistics of arbitrary number of points. So it's not a feasible way. Here comes the Markov process into play. If we are able, and it has been shown that we are able to show that this joint distribution of many velocity increments factorizes into conditional distributions with each, where each has only a single condition. So we have UR1 first scale condition on the second scale, and we continue this until we have the one before last scale condition on the very last scale, and for each of those we have the absolute velocity we have to add. Then we would have a much simpler problem here, because each of these PDFs is only a 2-point PDF plus the information on a single common absolute velocity. And actually this could be shown. This is not a very new result, so the first the paper on that was in 97, so it's quite some years ago. But the additional condition on an absolute velocity is a rather new result from, well, comparably new result from 2010. It could be shown that the additional condition on an absolute velocity makes the statistics much cleaner. This factorization of the n-point PDF into n 2-point PDF becomes much more clear. So this can be considered as a 3-point closure of the turbulence problem, but we have to point out it's a stochastic closure, because we are talking about PDFs here. It is not an analytical closure of the moment hierarchy in the Navier-Stokes equation. There is a difference. This is actually a colleague working on connecting both, but it seems to be challenging problem to out of this Markovian property to make a moment closure for Navier-Stokes equations. So I don't always see. But if we have a stochastic closure, we can write down a Fokker-Planck equation. The Fokker-Planck equation is like here. It's an evolution equation for PDFs. So it's because we are talking about PDFs, it's the right thing here. We can describe the evolution of these single, well, 2-point conditional PDFs over the scales. So here we have a D with respect to R. We can describe the evolution over scales by differential operators which operate actually in X, so on that axis. With this we have an equation for this stochastic picture of the turbulence statistics. That is actually a very successful approach for the stochastic view on turbulence. Still, it doesn't solve the Navier-Stokes equation, of course. There was a lot of results on that. To summarize basic features of laboratory turbulence, so homogeneous and isotropic HIT, is that the fundamental problem of possible solutions of the Navier-Stokes equation is not solved, but an advanced statistical description is available, which already helps a lot. We can now move on to wind turbines. How do they work? What is some basic working principles on them? Well, we have rather simple energy in the wind. Kinetic energy is, of course, 0.5 times the mass times the velocity squared, as with every kinetic energy. And as we know that, we already know the power in the wind, which is the derivative of the energy, which is, in this case, if we consider constant velocity, it's the mass change, so we have the derivative of the mass. In the power, we can take this a little bit further. Mass derivative is density times velocity. Actually, no, it's a volume. It's a volume derivative. Sorry. So density times volume is mass, and the derivative we consider the density as constant. So we have the derivative of the volume. Sorry, and this is clearly an area. So the cross-sectional area times velocity. We have the cross-section here because our turbine, of course, has a rotor area, which is the cross-section we consider, and the air moving through this cross-section is our mass and has a velocity. So we can derive the kinetic power contained in the wind as 1/2 rho times A times U cubed. So here we already have a typical U cubed dependency of wind power on velocity. So this is the power in the wind, and if we assume 12 meters per second, which is a lot, we have these velocities frequently for offshore locations, some 50 kilometers off the shore in the sea. We don't have them so frequently onshore, so but offshore we have it. Then we come to wind power of about 1 kilowatt per square meter as a rough estimate, which is funny because it is very similar to the solar power, which to the solar radiation power, which approaches the Earth at least on top of the clouds, especially today. We have a little bit less than 1 kilowatt per square meter down on the ground, but on top of the clouds, I think we will find. So the power of the wind turbine, the wind energy converter, WEC. The power of the wind turbine is, of course, not the full kilowatt per square meter, but we have to add a power factor, so a power is power coefficient. That's it. It's a power coefficient which is typically clearly below 0.59. There is a theoretical so-called Betz-Lukowski limit, which comes from the simple fact that if we build a wall and stop the wind completely, we do not extract the full energy from the wind. We rather extract nothing because there is nothing moving anymore. So we have to extract only a fraction of the wind, and the optimal fraction is 0.59. So we will never reach the 1 kilowatt per square meter. In this case, we would have as a maximum 590 watts. And real machines nowadays approach something between 0.4 and 0.5 as a power coefficient, but there is, I know of no single case where we cross the 0.5. So it's not trivial. Okay, so far simple considerations. Modern turbines have a size, well, 63 meters of radius is already a little bit outdated. These machines are from 5 years ago, more or less. We are now talking about rotors close to 200 meter diameter, so 180 meters like this. We have blades up to 80, 90 meters here, which is quite a size. But if we stick with the 126 meter diameter, we have an area of roughly 12,500 square meters, which gives a raw wind power of about 12 megawatt in our 12 meters per second situation. And if we consider the power coefficient, we will have something between 5 and 6 megawatts, and actually this class of turbines is the 5 megawatt class. There are French ones, there are German ones, there are American ones. The 5 megawatt class of turbines is used and manufactured nowadays almost all over the world. Okay, to compare with other machines, here we have our wind turbine. Typical average train engine of about 3 to 5 megawatt is more or less in the same class. So we are speaking about considerable amounts of power. We will never try to stop the train. And so this is already goes into the power plant range. This is no longer a small machine. Okay. Also compared to aircraft, because it's an aerodynamical machine, we could compare to aircraft. This is an A380. It's, of course, it came into the picture by Photoshop. This is not an approaching accident, but it has a span of, I think, something below 70 meters. And this thing has a span of 126 meters, so we are considerably larger than the largest passenger airplane. And we also are considerably cheaper, but that's a different story, because safety requirements are different for a passenger aircraft, of course, than for a wind. So these machines then have a power characteristic. Over the wind speed, we can display the average power we win, and this typically has in the beginning the U to the third characteristics, and then because with higher wind speeds the loads and the forces become larger and larger, we have to cut the amount of power, and it saturates to the constant rated power level. This is a power curve measurement, a very very typical thing done in the wind and busyness. Here we have the cut in. That means at this wind speed the machine begins to work at all. Here we have the rated, where we approach the saturation at the constant power level where the machine is designed for. And at some wind speed, which is typically 25 meters, it's up here, the machine switches off because forces become too large anyway. There's lots of wind energy on Earth, and it's becoming more and more. I think I don't need to elaborate this too much. This is also a little bit, but it's 2013, so it's not too old. We have 35 gigawatts in the EU we had 3 years ago, and the additional, this is installation, so newly installed wind power was 11 gigawatt, which is quite a lot, almost the same as PV, photovoltaics, by the way. So it's a growing field. We could think about, why talk about an industry branch which is growing, where people have business, everything seems to work, there are no problems. Why do science? That's a good question. These machines are actually designed for 25 years of lifetime, which is a nice thing. So you could think to buy one, you place it somewhere, and it runs for 25 years, but this is actually unfortunately not the case. Here we have failure statistics. On the left-hand side we have the number of failures per turbine per year. Here we have a zero line, and on the right-hand side we have downtime per failure, which is not so much important, but several components of the machines on average fail much earlier than in 25 years, once in 25 years. So we have, especially for the electrical system, and here it's especially the power electronics, we have about one failure every second year. That means after 2 years after installation you expect the failure of the power electronics. And this is still the case. I'm directly coming from the CEWIA conference. There were lots of presentations about everything, and also about failures of the converter system, and still half of, depending on the machine type, but more or less half of all the failures are due to the power converter system, and they have actually a failure every second year. So after erection only 2 years and the thing breaks down. That is, and the engineers designing these machines are not stupid, they do a good job. So there must be a fundamental problem about this. Why is nobody able to design a machine which lasts actually 25 years? Good question. Yeah, this is published data. Here we have, this leads, by the way, to operation and maintenance cost of about 1/4 of the total cost of energy. So the cost per kilowatt hour is, there is lots of cost for the machine and for cables and for putting up the machine and so on, but for operation and maintenance we have 25 to 30% of the total cost, because we have so many failures. And one reason we think that is in contrast to a classical power plant. Here we have a water power plant in southern Germany. These traditional power plants run in a steady state, in controlled conditions, and they can run for decades, for 50 and 100 years without problems, because they have controlled conditions, and the wind turbines don't have controlled conditions. So we are coming to the wind conditions here, to the third point. About wind conditions, about how turbulence connects to our wind turbine. And if we consider IEC is the international standard of the International Electrotechnical Commission. It is required that we measure the wind in front of the turbine, and this can be done. Typically we use meteorological towers like this. You will have a connection to metrology, so I don't need to explain too much. This is Fino 1, a famous German offshore measurement platform with a very strong power, with lots of influence on the anemometers, unfortunately, but still it's a tower, and we can measure a lot of things here. Traditional anemometers include especially cup anemometers, where we have 3 cups rotating, because the open cup has a higher drag coefficient than the closed cups are, so the thing can rotate in the wind flow. Ultrasonic anemometers are a little bit more sensitive. They are 3-dimensional. If we have 3 pairs of sonic transducers, and they can go up to higher frequencies. Classical method would be the bundle tube, but it's not really practical in the field. We have done some research to try to improve these atmospheric flow measurements. There is the so-called laser cantilever anemometer on the left-hand side. It is this one. It is using a tiny cantilever, much like the cantilevers in the atomic force microscope. So it's about